Okay, so now we're going to run through some of the basic gas laws. Okay, gases, like I said, they're real predictable. They do exactly what you expect them to do. It's kind of cool in terms of that. So what are the gas laws? Well, they're basically, the idea is if you have a certain amount of gas, so you don't change the amount of gas you have. If you change one of the variables, pressure, temperature, or volume, it will affect the other two variables. Okay, and there are going to be multiple gas laws that you're going to see, but then I will combine them into one, and that'll make your life better. One of the biggest things you have to remember is that the units have to match. Okay, when you're doing gas laws, the units are super important. Super important. So make sure you pay attention to what your pressure, volume, and temperature units are. The biggest thing is, anytime you're using temperature in a gas law, it has to be an absolute temperature. No matter what the problem says, it has to be an absolute temperature in order to use the gas laws. Okay? Once you're done using the gas laws, you can do whatever you want. And just to remind you, degrees Celsius plus 273 equals Kelvin temperature. So all you have to remember is that anytime you're using temperature in a gas law, it has to be in kelvins, not degrees Celsius. So the first law we're going to do is called Boyle's law. I don't personally care one way or the other if you know who it's named after. But Boyle's law says that the volume of a fixed amount of gas, and again, you're not messing around with how much gas you have inside the container, but and the temperature is constant, the volume is inversely proportional to the pressure. What it looks like in terms of a gas law is P1 times V1 equals P2 times V2, okay, for a gas held at constant temperature and constant amount. So, sample problem. The diver blows a 0.75 liter air bubble underwater. It rises to the surface. Pressure goes from 2.25 atmospheres to 1.03. Keep in mind, at sea level, it's about 1 atmosphere. Okay, that's called standard pressure. What will the volume of air in the bubble be at the surface? Okay, so what you have to do is you have to actually go through and identify P1, V1, P2, and V2. And I highly recommend this. If algebra is a challenge for you, literally, I would prefer you write this down. Okay, so 0.75 liter air bubble underwater. Okay, so I'm going to call that my volume 1, 0.75 liters. Now I need to find the pressure that corresponds to that particular volume. Well, as it rises to the surface, the pressure goes from 2.25 atmospheres, so that's where I'm starting, to a new pressure of 1.03 atmospheres. And what will the volume be at the surface? X. So that's your variables, putting in your numbers for your variables. Now, a couple of things I want to point out. Units have to match. If this was kPAs and that was millimeters of mercury, you have to turn one into the other, or you have to turn them into the same thing. It doesn't matter what you turn them into, because it's all multiplication, but they all have to be the same unit. So with that in mind, if this is liters, that means my answer is going to be in liters, which is fine because they don't specify. So setting it into the equation, you have 2.25 times 0.75 equals 1.03 times x. All you have to do is multiply those two numbers on the left and then divide by the coefficient of x. And you get with 1.64 liters. Now I want you guys to think about this for a minute, okay? Think of your little balloon and the ping pong balls. It is at a relatively high pressure, and it has that volume, okay? So pressure is pushing, squishing that gas, okay? Now, if I allow the gas to move to a lower pressure, it's not going to have as much squishing going on. It's not going to have as much pushing going on that gas. What's going to happen to the volume? Well, if you think about it, if I don't push it as much, it's going to expand in volume. And I have an answer that shows me that, yes, it did expand, okay? I would have expected it to do that. Since the pressure went from 2 to about 1, the pressure decreased by about half. The volume went up by a little bit more than 2. It's directly proportional, or sorry, inversely proportional. So the pressure went from 2 to 1. The volume went from 0.75 to a little bit greater than 1.5. So pressure went in half, volume doubles. Inversely proportional, and it's directly like it's a easy relationship mathematically. Okay, so go ahead and see if you guys can do this one. Okay, again, identify P1, V1, P2, and V2. All right, so if you look at this, here's my pressure, and it corresponds to a volume of that. And it's important to recognize your units, okay, whether it's pressure or volume or temperature. Just saying. So I'm going to call this 101.3 kPa. Notice I wrote the units down, 300 milliliters. Pressure 2 is 2 atmospheres, and I'm looking for the new volume, X. Okay, so now first thing I want to notice is that my units don't match. So I need to make them match. Doesn't matter which way you make them match, but I'm going to go this way. I'm going to say 1 atmosphere is 101.3 kPa, therefore I have a pressure of 1 atmosphere. Now I just want you to think about this for a second. The pressure went from 1 to 2. The pressure doubled. So the amount of pushing on this gas doubled. Think about what's going to happen to the volume. Well, if we plug it in, we have 1 times 300 equals 2x. X equals 150, and the units would be milliliters because the units are milliliters. And does that make sense? Well, yeah. If you're squishing a gas twice as much as you used to, the volume would be half what you expect it to be. Okay, inversely proportional. Okay, Charles's law we're going to save for the next movie.